Okay, the rest of the problems will focus on equation solving, inequalities, quadratic inequalities, and domain and range and family of functions. Here, both of these problems are quadratics. Whenever you're solving a quadratic, you have to set the equation equal to 0, factor, and solve. Once we have the equation equal to 0, we can go ahead and factor the problem. Using different factoring techniques, whichever you prefer, we can factor the problem into 3x plus 1, x minus 7 equals 0. Now we set each of these parentheses equal to 0, and that is how we solve to find out that x equals 7 and x equals negative 1/3. Problem on the right, we are going to approach the same way. However, on this problem, what ends up happening is that it is not factorable. When a problem is not factorable, we need to use quadratic formula. Quadratic formula is opposite b plus or minus square root b squared minus 4ac all over 2a. You could also use completing the square. However, on this problem, completing the square would be rather ugly, and I think quadratic formula would be much easier. After we plug everything into our formula, we get the following. From here, we want to simplify our radical, and our final answer will be negative 5 plus or minus square root 57 over 8. The problem on the left follows what we call a quadratic model. We notice that we have what looks very similar to a problem like x squared minus 12x plus 20. However, the problem that we are given doesn't use x. So what we are actually going to do is use a method of substitution. We are going to let x equal r to the 1/3 power. So now I can go ahead and factor this simpler problem into x minus 2, x minus 10, and I find out that x equals 2 and 10. But that's not my final answer. Remember, I want to solve for r. So what I'm going to do is take each of these answers and make them equal to r to the 1/3 power. And now I can solve these new mini problems. I'm going to solve them by taking each side and raising it to the 3rd power, and that is how I get 8 and 1,000 for my answers. The problem on the right is an inequality. When we are solving inequalities, you solve these just like equations. The only thing we need to remember is if you multiply or divide both sides by a negative number, you must flip your inequality sign. Pause the video and solve this problem. For this problem, I need to make sure that I'm careful with my negatives when I distribute, that I combine like terms on the same side first, and then I do the opposite to move terms to either side. In the second to last step, where I have to divide by negative 5, I have to flip my inequality sign because I'm dividing by a negative. And that's where I get my answer of x is less than 1. When we graph this on a number line, if we have simply a less than or a greater than, we use a parentheses. If we have a less than equal to or greater than or equal to, we are going to use a bracket. And then because it is left than, I draw my arrow to the left. As far as my interval notation, that's what we see here. The interval notation says that x values from negative infinity all the way up to 1, but not including 1, are solutions. For the problem on the left, we have a quadratic inequality. When solving a quadratic inequality, you first have to set the problem equal to 0, then you want to factor, then you're going to find those special numbers or critical values. So here, if I factor this, I get x plus 2, x plus 5 is less than 0. My special numbers are going to be negative 2 and negative 5. So now what we can do is we can make our plus minus chart. On our number line, we'll have a negative 5 and a negative 2, and then we write both of our factors, x plus 5 and x plus 2. The factor x plus 5 is going to be negative when x is less than 5, and it will be positive when x is greater than negative 5. The factor x plus 2 is going to be negative when x is less than negative 2, and it will be positive when x is greater than negative 2. Now I look at the product of these signs. If I do a negative times a negative, that gives me a positive product. A positive times a negative gives me a negative product, and a positive times a positive gives me a positive product. So this right here is the product which means multiply, of the signs in our sign chart below. Now, because this problem is a less than problem, things that are less than 0 are negative. Therefore, my solution set would be the values that are in between -5 and -2. Because there is no equals to bar, I would use parentheses here, and then I would color in the space in between. So my solution is -5 to -2. For this problem on the right, this is what we call a compound and problem. Think of it like it's a sandwich. So we look at what we need to do to solve in the middle, and then anything that we need to do, we do to all three sections of our graph. This gives us 16 less than or equal to 4x less than 26. Now I need to divide by 4 in the middle, so I do that to all sections of my graph. 4 less than or equal to x less than 13 halves. In interval notation, I would have a bracket on the 4 and a parenthesis on the 13 halves. The problem on the left is a rational inequality. When we are solving rational inequalities, you cannot cross multiply. And that was a common thing that people wanted to do in this chapter. You are not allowed to cross multiply. Instead, what we need to do is we need to set it equal to 0. We need to use lowest common denominators to combine the fractions. And then after we've done that, we go ahead and find our critical values. So here I'm going to subtract 2. And then in order to make these fractions able to be combined, I'm going to multiply it by an x plus 3 over x plus 3, so we have like denominators. So now everything is over x plus 3, and my numerator is 5 minus 2x minus 6, which gives me negative 2x minus 1 over x plus 3, less than or equal to 0. Now when I go to do my sign chart, the numbers that I'm going to use are any values that make the numerator or the denominator equal to 0. To find these, we can just set up our little mini problems and set those values equal to 0. And we get that those values are -1/2 and -3. Alright, so if we take a look at these two factors and take a look at how they behave, my x plus 3 factor is negative for values smaller than -3, positive everywhere else. My negative 2x minus 1 factor behaves differently. Since our negative is on the variable, my sign pattern actually flips here. So instead of seeing signs that start negative and then turn to positive, we actually see signs that start positive and then flip to become negative. I then look at the product of my signs. And then the last thing that I want to look at is what kind of answer I need to finish with. Since I want my problem to be less than or equal to 0, I need my negative signs in my result. And because I had gotten the value of -3 from the denominator, even though my problem has an equals to bar, I have to use a parenthesis here, because if I were to use a bracket, then that would give me a value that makes the denominator 0, which is not allowed. So my final answer is -infinity to -3 union -1/2 to infinity. When solving absolute value equations, we need to set up two different problems. First, we need to isolate the absolute value bars, and then we set up two equations, one where it equals the positive of the number, the other where it equals the negative of the number. In this problem to the right, I would first subtract 3 on both sides, giving me 2x minus 10 is equal to 4. Now I can set up my two different problems. 2x minus 10 equals positive 4, and 2x minus 10 equals -4. And we go ahead and solve these individually. After solving both of these problems, we see that our solutions are x equals 7 and x equals 3. When we have problems involving radicals, we need to get one radical on each side and square both sides. After rewriting this with one radical on each side, when we square both sides, the radicals will end up going away, giving us 2x plus 1 equals x. Now we just go ahead and solve this problem like normal. We have to make sure that any solutions that we get work in the original problem. Things to check for is whether or not it makes the radicals negative. In this case, a negative number inside the radical is not allowed, therefore this problem has no solution. If our problem were to be a little bit more complicated and have had something like, for example, an extra number off to the side, then when we square both sides, we would have to make sure that we FOILed. So in this case, we would square both sides, and that would give me the radical squared, which is just 2x plus 1, double the product, so plus 6 radical 2x plus 1, and then the last term squared, which is 9, and then the right hand side would just be equal to x. And then from here, we would re-isolate this radical and square both sides again. When we're dealing with absolute value inequalities, we need to remember our rules. With a less than problem, remember we pronounce it as less than, and. So we want to go ahead and we want to rewrite this as an and statement. When we write it as our and statement, what we are going to do is we will have first our original problem, 2x minus 3 less than 4, and then the 2x minus 3 stays the same, that doesn't change, but we switch the inequality sign and we change it to be negative 4. And then we go ahead and we solve both of these individually. We get x is less than 1/2 and x is greater than negative 1/2. And if we look at these on a number line, negative 1/2 and 1/2, we are going to have the area in between negative 1/2 and 1/2. Now for a greater, we want to pronounce it as greater, greater. And just like we did for our and problem, we rewrite the inequalities. The part inside the bars never ever changes. The only part that changes is the part that is after the bars. So here I would have a less than or equal to and a negative 8. And then now I go ahead and I solve each of these individually. And I have that x is greater than or equal to 6/5, so bracket and to the right, or x is less than or equal to negative 2, bracket and to the left. When solving rational equations, we want to find the lowest common denominator and multiply it on all terms. For this problem, our LCD is 4 times x minus 1. So we are going to multiply 4x minus 1 on all terms. What ends up happening is that the terms that are fractions, the denominators will cancel, and any terms that are not fractions, you'll just have to multiply through. The resulting problem is x minus 1 times x plus 2 minus 5 times 4 times x minus 1 equals 3 times 4, or 12. After distributing, we get the line that is in purple. From here, because I have an x squared, that means I have a quadratic, so I need to set my equation equal to 0 so that I can factor and solve. Once I get to this point, I have a quadratic, and this is not factorable, so I would then use quadratic formula. After solving with quadratic formula, we get the following expression. Things to check for are whether or not the answer we got makes our denominator equal to 0. In this case, the only value that is not allowed is 1. So if 1 would have been a solution, then I would have had to cross it off. When asked to find the discriminant and the type of solutions for a quadratic, you need to first make the equation equal to 0 and identify your a, b, and c. The discriminant is b squared minus 4ac. It is the quantity that is inside the radical before the quantity has been square rooted. If the discriminant is positive, there are 2 real solutions. If it's equal to 0, there is 1 real solution, and if it is negative, there are 2 imaginary solutions. Try the 2 examples below. In the first problem, we get a discriminant of negative 59, which means there are 2 imaginary answers. In the second one, our discriminant is 209, and that means we have 2 real solutions. Since 209 is not a perfect square, these solutions will be irrational. If I had gotten a perfect square, such as 100, then those 2 solutions not only would be real, they would also be rational. When we are trying to determine if something is a function, we look to see if each x has only 1y. So looking at a table of values, we basically check to see if the x value repeats. That would be the same as if we had a series of points. If we were looking at a graph, we look to see if it passes our vertical line test. So for example, this function does pass the vertical line test. Anywhere on the graph that I were to draw a vertical line, it would only intersect the graph once. If I were to draw the graph of, say, a sideways parabola, that would fail the vertical line test because one vertical line intersects my graph twice. So this right here would not be a function. When you are looking at an equation and you're trying to determine if an equation is a function, things that we talked about in class, we're looking for when your y has absolute value bars around it, or if your y value is squared or raised to any other even power. The reason why this results in something that is not a function is because negative and positive y values will return the same x value, and the same x value can only be associated with one y value. When we talk about our family of functions, we talk about the different shape of the graph and also its translations. Here we will see the first four graphs. For my linear function, both the domain and the range is going to be all reals because the graph extends left and right and up and down forever. Your linear functions are ones that look like a line. Your quadratic function is going to look like a U or a parabola. And in this graph, your domain is going to be all reals, and your range will be connected with the y value of your vertex. In this graph, let's say this goes through the point 0, 0, my range would be 0 to infinity. If I were to have taken my parabola and let's say moved it up and over, and maybe this y value were say 10, then in that case my range would be 10 to infinity. So for quadratics, your range is connected to the y value of your vertex. If my graph were flipped over, and let's say this value were -3, then my range would be negative infinity to -3. When we're looking at absolute value graphs, absolute values look like these, and they behave the same way as quadratics in terms of domain and range. The domain is all reals, and the range is connected to the y value of your vertex. If your graph is flipped over, then just like we saw over here on our quadratics, your range is essentially flipped over. My square root graph looks like half of a parabola. Since we know we cannot take the square root of a negative number in our real number system, the domain is 0 to infinity, and our range is also 0 to infinity. Alright, let's go ahead and erase all this so that we can write in more functions. We also talked about the cubic graph and the cube root graph and our greatest integer function. For our cubic and our cube root, both of these have a domain and range of negative infinity to infinity. For our greatest integer function, what happens is our y value rounds up to the greatest integer x has already equaled. Visually, it looks like a series of barbells where we start with a closed circle to an open circle. And these barbells are 1 unit in length and step up 1 unit at a time. When we talk about our translations, we say that for any function, let's just use a parabola for example, we have a times x minus h squared plus k. We say that the vertex, or you can think of like your anchor point, is at hk. So these two values right here tell you how your graph moves for the h value, left or right, and for the k value, up and down. The a value is going to be your vertical multiplier. If we happen to have a coefficient in front of the x, this is going to give you a horizontal shrink or stretch. We did a ton of examples like this back in Chapter 2, and we had numerous worksheets, so make sure that you look at your Chapter 2 worksheets for more examples on graphing. Last but not least, domain and range with regards to just equations only. In these three problems, we want to be able to determine at least the domain and in some the range for these functions. The first graph is a square root function, and we know that square roots have to have positive values inside the radical. So I would set x minus 15 to be greater than or equal to 0, giving me that x is greater than or equal to 15. I know visually that my y values for a radical are always going to be positive. So I know that my domain will be from 15 to infinity, and my range will be from 0 to infinity. The next graph is an absolute value v. Visually, I know that this graph goes 1 to the right and up 4. And I know it's going to look like this. Domain for absolute value graphs is always all reals. The range is affected by the y value of the vertex. Since the graph moved up 4 and it still faces up, 4 is the smallest value and the graph stretches up to infinity. This last one down here is a rational function. We will learn how to find the range for these second semester. For right now, we just want to make sure you can find the domain. And to find the domain, you look at your denominator. In this problem, x is not allowed to equal negative 1. So I would write my domain as negative infinity to negative 1, union negative 1 to infinity. And basically what this is stating is that all values except negative 1 are allowed. This is not at all everything that we've learned. Don't forget to do your basic linear equations, how to find slope, slope-intercept form, point slope, how to write equations of your lines. Remember our horizontal and verticals, the HOI-VUX acronym. Function composition, that would be like your f of g, stuff like these are function form. So definitely make sure you go through and work on the packets, look back over your chapter notes, and really dedicate some time to quality study.